Today we are going to deal with derivatives of implicit functions. What are implicit functions? Functions can be represented in a variety of ways. Most of the functions we have dealt with so far have been described by an equation of the form y equal to f of x that expresses y in terms of the variable x. It is not always possible to solve for one variable explicitly in terms of another. Those cases where it is possible to solve for one variable in terms of another to obtain y equal to f of x or x equal to g of y are said to be in explicit form. If an equation in x and y is given, but x is not an explicit function of y and y is also not an explicit function of x, then either of the variables is an implicit function of the other. Let us directly get into the examples. Here we are asked to find dy by dx, and these are all the examples. So what we note in all these examples is we cannot express either x in terms of purely in terms of y rather, or y purely in terms of x, and hence these are all implicit functions. So we start with the first one. We are given x raised to 5 plus xy cube plus x square y plus y raised to 4 equals to 4. And what we do in the derivatives of implicit functions is that we just simply differentiate each and every term, just making use of all the possible laws of differentiation and the rules of differentiation. So differentiate with respect to x. So first term is x raised to 5, therefore it is d by dx of x raised to 5. Second term is xy cube, so it is d by dx of xy cube. And so the next term is derivative of x square y plus derivative of y raised to 4 equal to derivative of 4. So derivative of x raised to 5 is 5x raised to 4. And here in this part of the function we make use of product rule here, here as well as here, and here we think of composite rule. Since y is a function of x, so we treat y raised to 4 as x raised to 4, then its derivative gives you 4y cube into derivative of what you thought as x, that is y. And rest of the things here are just we have made use of product rule. So the derivative of y cube is 3y square into dy by dx, and here the derivative of x is 1, and this is dy by dx, and again here it is derivative of x square is 2x, this is as it is equal to 0. So in this step what we have done is we have collected all dy by dx term to the left hand side and shifted non dy by dx to the right hand side. It is always preferred to keep the dy by dx terms on the left hand side and non dy by dx on the right hand side. Not necessarily all in every problem should be done like this, but wherever you feel that it's comfortable, it is better to keep this way. So take dy by dx out, and in the right hand side take the minus sign out. Therefore we get dy by dx equal to minus of 5x raised to 4 plus 2xy plus y cube upon x square plus 3xy square plus 4y cube. Next one, it is a combination of exponential and logarithmic functions. Differentiate the function as it is. So therefore it is d by dx of x square plus d by dx of e raised to xy equal to derivative of y square plus derivative of log of x plus y. And so this is the derivative. So here again a composite function rule is used. E raised to xy, we treat xy as one unit, something like u, e raised to u. Derivative of e raised to is e raised to u into derivative of what you thought as u. So next step we are going to make use of the product rule here, and this is 2y dy by dx plus log of x plus y, derivative is 1 upon x plus y into derivative of what you thought as x or u, that is x plus y. So that is 2x plus e raised to xy, x dy by dx plus y into derivative of x is 1. These two terms, this term is as it is, and here derivative of x is 1, derivative of y is dy by dx. So here open the bracket on both left hand side as well as right hand side. Here this e raised to xy gets into the bracket, and here 1 upon x plus y gets into the bracket. So next step is what we have done, that we have taken dy by dx to the right hand side. So that gives you 2x plus y e raised to xy minus 1 upon x plus y equal to 2y dy by dx minus x e raised to xy dy by dx plus 1 upon x plus y dy by dx. So we have taken dy by dx term out here, and next step is that we are going to take LCM in the left hand side as well as the right hand side. So here in the left hand side x plus y becomes the LCM, so it gives you 2x into x plus y plus y e raised to xy into bracket x plus y minus 1 equal to, similarly we do the same thing in the right hand side, and that gives you 2y times x plus y minus x e raised to xy times x plus y plus 1 upon x plus y. And what we find is x plus y common on both the sides, so the common factor, those two factors can be cancelled, and then what we get is dy by dx equal to 2x times x plus y plus y e raised to xy times x plus y minus 1 upon 2y times x plus y minus x e raised to xy times x plus y plus 1. So this is a problem involving trigonometric function, differentiated function as it is, and now it's the usual normal differentiation, derivative of every term is considered, and here these two functions are composite functions, this and this one are the composite functions. So there we make use of the composite rule. So derivative of cos xy minus sin xy into derivative of xy. Derivative of sin x plus y is cos x plus y into derivative of x plus y. So that gives you 3y square dy by dx minus sin xy, and here again we make use of product rule and here addition rule. So we open the bracket in the left hand side as well as the right hand side, and that gives you 3y square dy by dx minus x sin xy dy by dx minus y times sin x plus xy equal to 2x minus cos of x plus y minus cos of x plus y dy by dx. Again we have collected dy by dx terms on the left hand side, so that gives the expression like this, that is 3y square dy by dx minus x sin xy dy by dx plus cos x plus y dy by dx equal to 2x plus y times xy minus cos of x plus y. So take dy by dx out in the left hand side and cross multiply, we get dy by dx equal to 2x plus y times sin xy minus cos x plus y divided by 3y square minus x sin xy plus cos x plus y. In the fourth one, it is given that 3 raised to 2x plus 3 raised to 2y equal to 3 raised to 2 times x plus y. We call it as equation 1. Only in this example what I am trying to do is how the problem can be simplified. That part I am going to explain towards the end. So therefore it is considered as equation which we are going to make use of once again, that equation. So differentiate equation 1 with respect to x. So that gives a normal differentiation, derivative of each term, and this is the derivative of 3 raised to 2x as 3 raised to 2x log 3 into derivative of 2x plus derivative of 3 raised to 2y is 3 raised to 2y into log 3 into derivative of 2y, 3 raised to 2 times x plus y log 3 into derivative of 2 times x plus y. So derivative of 2x is 2, derivative of 2y is 2 dy by dx, and here this 2 goes out, the derivative of x plus y is 1 plus dy by dx. So what is important and a point to be noted here is, we find 2 times log 3 is common throughout, so we divide throughout by 2 times log 3 and collect the dy by dx term on one side, that is on the left hand side, and non dy by dx terms on the right hand side, and take dy by dx out in the next step. It is 3 raised to 2y minus 3 raised to 2 times x plus y dy by dx equal to 3 raised to 2 times x plus y minus 3 raised to 2x. Now cross multiply, that gives you dy by dx equal to 3 raised to 2 times x plus y minus 3 raised to 2x upon 3 raised to 2y minus 3 raised to 2 times x plus y. And here the next step is to be noted, that is this step. So what is done here, note it very carefully. So what is done here is we have replaced 3 raised to 2 times x plus y by 3 raised to 2x plus 3 raised to 2y. Similarly in the denominator here also this has been replaced by 3 raised to 2x minus 3 raised to 2y, because this minus sign gets in and so it becomes negative. This is with the help of equation 1. And in the numerator 3 raised to 2x get cancelled, in the denominator 3 raised to 2y get cancelled. So we get minus 3 raised to 2y upon 3 raised to 2x, and that's equal to minus 3 raised to 2 times x minus y. So again a simple problem, differentiate with respect to x. In the left hand side, and for both the terms we are going to make use of product rule. According to the product rule, it says x times d by dx of e raised to y plus e raised to y into derivative of x, and here y into derivative of e raised to x plus e raised to x into derivative of y, and the derivative of 1 is 0. So derivative of x and e raised to x are written here in the next step. We collect dy by dx term in the left hand side and take dy by dx out, and in the right hand side we find minus e raised to x minus y e raised to x minus e raised to y. So then cross multiply, that gives dy by dx equal to minus of y e raised to x plus e raised to y upon x e raised to y plus e raised to x. And here you are asked to prove that dy by dx equal to y by x, and the problem is x raised to m into y raised to n equal to x plus y whole raised to m plus n. So this is what we are given. So taking log on both sides, we get log of left hand side x raised to m into y raised to n equal to log of the right hand side x plus y whole raised to m plus n. So why log is taken to this problem? We have taken log on both sides. Why? Actually we take the log as the log to the problems whenever the problems are having complicated expressions involving too many products, quotients, powers, etc. Or if you have base and power are functions of x, or both are functions of y, or base and power are functions of each other x and y. In such cases we generally take log on both sides. Though this problem does not belong to any of those category, we are going to take log on both sides only for the sake of convenience. This is the point to be noted. So left hand side it gives you m log x plus n log y equal to m plus n log of x plus y on the right hand side. Now differentiate with respect to x. Normal differentiation, they were derivative of h every term. So m and m plus n are constants, they are kept outside. So derivative of log x is 1 by x, derivative of log y is 1 by y dy by dx, and derivative of log of x plus y is 1 upon x plus y. So this is the previous step, m by x plus n by y dy by dx equal to m plus n upon x plus y dy by dx of x plus y. And now we are going to write the derivative of x plus y, and that is m by n upon x plus y times 1 plus dy by dx. And here we take this m plus n upon x plus y inside the bracket, and that gives you this step. And in the next step we are going to rearrange the terms, that is we shift dy by dx term from right hand side to left hand side, and non dy by dx term from left hand side to right hand side. So that gives you this step, and here we take dy by dx out, so it becomes n by y minus m plus n upon x plus y dy by dx equal to m plus n upon x plus y minus m by x. In the left hand side as well as right hand side we take LCM. So in the left hand side the LCM is y into x plus y, so that gives the numerator as n times x plus y minus m plus n times y into dy by dx equal to right hand side x into x plus y as the LCM in the denominator, and that gives m plus n into x minus m into x plus y. Open the brackets. In the left hand side ny ny term get cancelled. In the right hand side, mx term get cancelled. So we are left with nx minus my upon y into dy by dx equal to nx minus y my upon x. So we can get cancel these nx minus my term from both the sides. We get therefore dy by dx equal to y by x. And the next problem is sine of px raised to m minus qy raised to m upon px raised to m plus qy raised to m equal to r. Then show that dy by dx equal to y by x, where r is a constant. Given that, we write this expression as it is. Then we shift sign towards the right, so it gives you sine inverse of r. R is a constant, so sine inverse of r is also a constant term. And so what we can substitute for sine inverse of r is a t. Again, t is again a constant term. Px raised to m minus qy raised to m upon px raised to m plus qy raised to m equals to t. Let us put sine inverse of r equal to t. Cross multiply. This denominator is multiplied here, and that gives ptx raised to m plus qty raised to m. Now rearrange the terms. So we always try to make y term positive. So I get px raised to m minus ptx raised to m equal to qy raised to m plus qty raised to m. So x raised to m is taken out in the left hand side and y raised to m is taken on the right hand side. So we find y raised to m equal to p times 1 minus t upon q times 1 plus t into x raised to m. So again observe p, t, q, they are all constant terms. So ultimately this expression will be another constant. So I will replace it by m and I will call this equation as 1. So here, replace it by s. This is s, not m. So s is what? P times 1 minus t upon q times 1 plus t. Now differentiate with respect to x. So that is derivative of left hand side equal to s times the derivative of right hand side, expression that is x raised to m. So my raised to m minus 1 dy by dx equal to s m x raised to m minus 1. On both the sides those m's get cancelled and we find dy by dx equal to s times x raised to m minus 1 upon y raised to m minus 1. This s is replaced by y raised to m upon x raised to m, and that is with the help of equation 1. From 1 we have s equal to y raised to m upon x raised to m, and therefore we get dy by dx equal to y by x. Second inverse of x cube plus y cube upon x cube minus y cube equals to 2a. Then we are asked to show that dy by dx equal to x square tan square a upon y square. And here the point to be noted is dy by dx contains ax term containing a. So it clearly says that we are not going to eliminate a from this problem where a is a constant. So we know that sec inverse of x is equal to cos inverse of 1 by x. So using that formula we can write it as cos inverse of x cube minus y cube upon x cube plus y cube equal to 2a. And cos inverse is shifted to the right hand side, it gives you cos 2a, and then cross multiply this denominator over here, and that gives you x cube cos 2a plus y cube cos 2 in the right hand side, x cube minus y cube in the left hand side. Again rearrange the terms keeping y as positive, so minus y cube comes to the right hand side and x cube cos 2a goes to the left hand side. So that gives you x cube minus x cube cos 2a equal to y cube plus y cube cos 2a. So take x cube and cos cube terms out, that gives you x cube into 1 minus cos 2a equals to y cube into 1 plus cos 2a. Therefore y cube equal to 1 minus cos 2a upon 1 plus cos 2a times x cube. 1 minus cos theta is 2 sin square theta by 2 and 1 plus cos theta is 2 cos square theta by 2. Therefore this gives you 2 sin square a upon 2 cos square a times x cube. 2 to get cancelled. So we get y cube equal to tan square a x cube. Now differentiate with respect to x. So this is the derivative of y cube in the left hand side. Tan square is a constant, so it is kept out into derivative of x cube. So that gives you 3y square dy by dx equal to tan square a times 3x square. And again 3 get cancels, we get dy by dx equal to x square tan square a upon y square, which is the required result. And next is that if root of 1 minus x square plus root of 1 minus y square equal to a times x minus y, then show that dy by dx equal to root of 1 minus y square upon 1 minus x square. And here also, though it is not given, we consider a as a constant term. This is the given expression. So we substitute x equal to sine alpha and y equal to sine beta. Therefore, we get alpha equal to sine inverse of x and beta equal to sine inverse of y. Therefore, the given equation 1 becomes root of 1 minus sine square alpha plus root of 1 minus sine square beta equal to a times sine alpha minus sine beta. So the left hand side reduces to cos alpha plus cos beta equal to a times sine of alpha minus sine beta. And in the left hand side we make use of the formula cos c plus cos d, and in the right hand side we make use of the formula sin c minus sin d. Cos c plus cos d is 2 cos c plus d by 2 into cos c minus d by 2, and sin c minus sin d is 2 cos c plus d by 2 into sin c minus d by 2. So that gives you 2 cos of alpha plus beta upon 2 cos of alpha minus beta upon 2 equal to 2a times cos of alpha plus beta upon 2 into sin of alpha minus beta upon 2. And therefore cos of alpha minus beta upon 2 equal to a times sin of alpha minus beta upon 2, because we get cancelled those 2 cos alpha plus beta upon 2 from both the sides, and that implies cot alpha minus beta upon 2 equals to a. Therefore alpha minus beta upon 2 equal to cot inverse of a, and cross multiply that 2, so we get alpha minus beta equal to 2 cot inverse of a, and replace back the values of alpha and beta, that is sin inverse of x minus sin inverse of y equal to 2 cot inverse of a. Now differentiate with respect to x. So that is derivative of sin inverse of x minus derivative of sin inverse of y equal to derivative of 2 times cot inverse of a. Right hand side is a constant term, so its derivative becomes 0, and on the left hand side it is 1 upon root of 1 minus x square minus 1 upon root of 1 minus y square dy by dx. Therefore 1 upon root of 1 minus y square dy by dx equal to 1 upon root of 1 minus x square. So dy by dx equal to root of 1 minus y square upon root of 1 minus x square, and we can club the right hand side as under single root, and that is dy by dx equal to square root of 1 minus y square upon 1 minus x square. If y equal to root of tan x plus root of tan x plus root of tan x up to infinity, then show that dy by dx equal to x square x upon 2y minus 1. This is an interesting problem. So given that the given expression we have written as it is, and we call it as equation 1. So squaring both sides, we get y square equal to tan x plus root of tan x plus root of tan x plus dot 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 up to infinity. So this is actually same as, if you carefully note this, here I have got infinite number of terms, and there is no harm in extending one more term within the square root. So I write it as y square equal to tan x plus root of tan x plus root of tan x plus root of tan x up to infinity. And again, if you carefully note, this is nothing but the equation 1, which is nothing but y. Therefore we get y square equal to tan x plus y, that is from 1. Now differentiate with respect to x again. So that is a derivative of y square is in the left hand side, and derivative of tan x plus derivative of y on the right hand side. So that is 2y dy by dx. This dy by dx is shifted to the left hand side, so it becomes 2 dy by dx minus dy by dx equal to x square x, derivative of tan x. Take dy by dx out, 2y minus 1 dy by dx equal to x square x. Therefore dy by dx equal to x square x upon 2y minus 1. Thank you.